But what we want to do today is to go into talk about introduction. So I'll be so the next title of the presentation is Introduction to ISIs, as you all see over there. I got into town a little bit late, and I'm still lacking enough sleep. So sorry for any potential sleep as we go along. But this will be just introductory stuff. I have lots of slides up to like about 104, which probably stretches into some of the advanced concepts. And there was no way I could take them out. I just wanted them to be there just in case anybody could use them. I mean, this could be a reference for the future. So you're going to see lots of slides. I mean, if we can go through them, all then sure we'll try to. We have just 90 minutes to do all of these. I'm going to try to go as fast as possible, but the key thing is for you to grasp the concept. And so if you have any questions, feel free to stop me. I wouldn't mind, doing just half of the slides if you go away, with some complete understanding of the subject matter. So let's do that. So these are the topics that we plan, to cover here in this session. We want to do an overview of the ISIS routing protocol, and then go on to touch on some basic concepts. And then probably one of the most challenging things about ISIs is the additional addressing scheme that people have to be familiar with. So you normally are configuring ISIs for an IP environment, and you still have to configure some CLNS address in there, and sometimes people get intimidated by that. So we'll do that a little bit. And then the next thing we want to do is the ISIS database. And then touch on MPLS traffic engineering extensions for ISIS. Look at some network design considerations, and then go on to talk to look at some configuration examples. And we'll do again, some basic troubleshooting because we don't have enough time to do that. And then I'll have some slides here which point to references for further reading. Now, can everybody hear me? Am I speaking too fast or slow enough? Okay, so before we go into this, okay, so we just wanted, ISIS has its roots in some ISO. Okay, you think this may work better? Okay, so probably there's a conflict here. Here, that should turn this guy off. Hello? So probably okay, good. Okay, so like I said before, ISIS has roots in ISO. Yeah, because it looks like this is not working, and I had to go back to this other one. So what should I do? Yeah, okay, I thought it was going to be, hello? Yeah, okay, it's up. Okay, so lots of gadgets, plus lack of sleep, all right, it makes the situation a little bit complicated. All right, so let's go into a couple of technologies. Okay, that one is gone.
That one doesn't appear to be on, but let's see.
Maybe I should just pull this.
So it goes all together.
Okay, good.
You're not going to need those, are you? I mean,
No, I don't need those. I'm going to switch it in. Okay, so probably this is a lot better now. So let's go into some terminology here. Being in the router IP world, you're familiar with routers, right? In ISO, when you go to read the ISO 10589, this will be intermediate systems. So anywhere you run into intermediate systems, that means a router. And then there is a designated intermediate system, which has the same notion as a designated router. So it looks like. Maybe I can just do that on microphone. Throw all these gadgets. Oh, but they need to record, so let's try again. Okay, so the other terminology here is pseudo node, which stands for a sort of emulation of your broadcast LAN. So a DR plays the role of what we call a pseudo node. So in ISO, all your routers are intermediate systems, and they are referred to as nodes, right, in a network. And so the pseudo node implies some virtual node. And what it means is that we take the whole LAN, for instance, let's look at the broadcast multi-access network, and we try to represent that. And I have a slide to show that. But we take a broadcast multi-access network and represent that with another virtual node, right? And then an end system is your regular workstation or network host. And then the other terminology here is network service access point, which stands for network layer address. And then there is the subnetwork point of attachment, which is a data link interface. It will be your MAC address, for instance. And then there is this notion of a packet data unit, the same thing as a packet. And then the link state packet data unit means routing information packet. And so we'll talk about some of this as we go on. So for an overview of ISIS, ISIS stands for Intermediate System to Intermediate System Routing Protocol. And this was originally designed for routing in an ISO connectionless network using the CLNP protocol. Right? So we had a CLNP protocol just like IP, and we needed to do dynamic routing because we couldn't always be doing a manual route. Just like in IP, people came out with routing protocols, right, to kind of help dissemination of routing information. And so somewhere later in the years, this was adapted to carry IP information, and the RFC for that was 1195, and it was also just about the same time that OSPF was being developed. And what this was called is the integrated ISIS or dual ISIS. Dual ISIS because you can use the same protocol to run ISO, CLNP, as well as IP if you wish to do that. In most networks today, ISP networks, probably that doesn't really matter anymore. Most people use it for just IP, routing IP. You still have a little bit of the CLNS stuff in the background because the whole idea is based on watching the node, and we carry the IP routing information as additional information. So when you configure ISIS, you would see a lot of CLNS in there. And we'll look at some configuration examples down the road. So we all know that ISIS is a link state protocol just like OSPF. And the only difference again is that OSPF supports IP and ISIS supports both IP and CLNS. I believe that somewhere at the last NANOG, Descartes did some presentation comparing the two protocols, so I'm not going to go into that. The goal here is to give you a basic understanding of how the ISIS protocol works. Now we also know that the ISIS is an interior gateway protocol, meaning that it's designed to work within a domain. So if you have an autonomous system and you need the routing protocol to back up BGP, we would use ISIS or OSPF, right? Now for our interdomain routing, everybody uses BGP today. And then for those interested in the CLNP aspects of ISIS, if you need to do interdomain routing, then you can use the protocol, the Cisco proprietary protocol called ISO IGRP. So the basic, so we start with CLNS, which is the ISO protocol for connectionless networking, all right? And that protocol, CLNS is not a protocol, but CLNS as a way of networking using connectionless connectivity between network nodes is based on 3 protocols. One of them is CLNP, which is the equivalent of IP, and then there's ISIS, which we are going to be talking about. And then there's another protocol called ESIS, which is End System to Intermediate System Routing Protocol. And that's for communication between workstations or end systems and the routers. We wouldn't really talk much about that because I guess the interest here is to understand how ISIS works on routers and in IP networks. Okay, so the other interesting thing is that unlike the other protocols that go over IP, for instance, OSPF or ESGRP, ISIS is a network layer protocol by itself, and it just goes over the data link, right? So that's a very key difference between ISIS and OSPF right here. So these are some references to the various specifications that will give you a lot more information about how about this protocol. So there's CMP, ESIS, ISIS, and they all have RFC versions of the ISO documentation, right? So for instance, for ISIS, we have 10589 and there's RFC 1142. Now there are 2 types of hello protocols or hello systems that operate within the ISIS environment, and one of them is the ESIS kind of communication. And here we use end system hellos and intermediate system hellos. And then there's also IIHs, which stand for intermediate system to intermediate system hellos. And so normally for routers to discover each other and talk ISIs, they use IIHs. If a host needs to discover a router, then it would send an ESH and the router will respond with an ISH. So this last bullet implies that somehow we have ESIS tied into ISIS. For instance, on point-to-point links, before we send an IIH, we wait till we have received an ISH. Sorry, that's confusing. Okay, so now we go into the basic concepts, right? So we'll look at the types of nodes that ISIS supports, the links, types of links. We'll look at ISIS areas and adjacencies, and then talk about hierarchical routing, which is level 1 routing and level 2 routing. And so we have our regular hosts, which are our workstations. And in this case, since we are routing ISIS in an IP environment, it doesn't really matter. Hosts don't matter here. Because our host in the IP environment will be running some protocol like ARP or whatever to talk to their nearest connected router, right? But what's interesting here is the level 1 routers and level 2 routers who has an ISIS. And then we talked about the virtual nodes on the LAN, and we said there are level 1 and level 2 nodes. All right, so this is what it looks like for the node emulation that we talked about. We, for instance, have 4 routers on the LAN, right? And we all know the problems with N squared adjacency, I think it's called. But what happens here that we don't want all the nodes, right, to be talking to each other, even though in some way it happens in ISIS. For the sake of synchronizing our flooding, we emulate this LAN network with what we call a pseudo node. And one of the routers is selected to perform this role of pseudo node. And what this node is going to do is to conduct the flooding or coordinate flooding and synchronization of the LAN so that everybody would have synchronized databases. One of the key things about link state protocols is to have databases of all the routers in an area at least synchronized. So this is the role played by the disk. Now the disk here in ISIS is elected by interface priority. And if interface priorities are the same, then we choose the disk with the highest MAC address. right? Or SNPA that we talked about before. And there's only one disk also, right, which is also very interesting. But that's because we don't need, we have reliability kind of achieved in a certain other way, and I'll go on to talk about that. But there's only one disk, there's no backup disk. If that disk dies, another disk is selected right away. Types of links in ISIS, we have basically two types of links, right? So there are point-to-point links, which could be a packet over SONET, serial link, DS3, point-to-point frame relay if you decide to configure your multi-access networks to be that way, point-to-point ATM, and then we have broadcast links, which is typically your multi-access links, right, media. And so that's Ethernet multi-point frame relay, ATM or GPC Cisco. So we don't really have the notion of non-broadcast multi-access and as a network type, right? Something that probably you'll see in OSPF. So what are areas? All the ISI's domain is carved into areas. And so we have here on this slide, looks like I have to say somewhere here like that. We have here on this slide, we're showing three areas, and there's area 49.001, 49.002, and 49.003. So here we have the areas. Okay, so these are three distinct areas, right? And when we go to talk about ISIs or CLNS addressing, you would come to understand why I'm going to say this. But point is that every node can be in only one area, right? There are other things that can happen, with regard to having a node use multiple areas or area IDs. But at the end of the day, we get the whole area meshed into one big area. So every node has to be in just one area. And the only way we get a node to talk across to other areas is by doing what we call layer 2 routing, and that's because they connect to another node who comes from another area. So you exchange hellos, right, and you find out that this other node is in a different area. In that case, you bring up a level 2 adjacency instead of a level 1 adjacency. And so what we show here is three different areas with a backbone, right, between them. And as you can see, the nodes that are in the shaded area are level 1 and level 2. They have to be able to talk level 2 between themselves, and they have to be able to talk level 1 to the nodes that are just in the area and don't have connectivity outside. Right. So adjacencies. So it looks like we lost that. Can you guys still hear me? All right. Okay. So the adjacencies. Okay. So we said there are three types of hellos, right? For others to form ISS adjacencies, they need to exchange hello packets, and we have three kinds of them. One of them is the point-to-point hellos. The other is LAN level 1, and the other is LAN level 2, right? On point-to-point links, it doesn't really matter whether you are level 1 or level 2. We just need to establish adjacencies, and we do that. On the LAN or multi-access links, though, we need to differentiate between level 1 hellos and level 2 hellos, because you form level 1 adjacency based on what you get. All right, so this is the format of an ISI's hello packet for point-to-point links, or the point-to-point hello format. And we're going to we would look at ISI's packet formats again, but this is just to show you what goes into a hello packet for exchange on point-to-point links and to bring up a point-to-point adjacency. First of all, here we have the intra-domain routing protocol discriminator, which is just a number assigned to ISIS, and this is number 0x83 or 131 in decimal. And there is a length indicator which gives you the length of the header, because different ISIS packets have different header lengths, right? So we need to first of all be clear on what part of the packet is going to be our header. And then if you look at all the way at the bottom, there are what we call TLVs over there, and so after the header, right? So we always have a fixed header, and we have the TLVs over there. And then there's a version or protocol ID, which is 1, because there hasn't been any update on the protocol, and I know there's work going on to come up with a version 2. And then the ID length is the ID of the length of the system ID. So every node in an area, every node in a domain must have the same system ID length, right? So normally this is 6 bytes and has some root in gossip and stuff like that, government, open system, interconnection profile or whatever. But this is normally 6 bytes, right? And there's another version which is still 1. I don't know why we have 2 versions in there. And the next field is reserved. Then the maximum area addresses. So normally we said each node must be in one area. You can be by default also in 3 different areas, or you can be in a lot more, up to 255. And the holding time is the duration. The holding time tells you how long you would wait before you declare neighbor down if you don't receive a hello, right? So normally this holding time is made up of 2 parameters. One is the hello interval, which is 10 by default on Cisco's, and you normally exchange 3 hellos, right? Just like a keep alive on your serial link, you don't get 3 keep alive and you think the link is down, right? Or the protocol is down. So we have the hello interval, which is 10 by default, times an ISI's hello multiplier, which is 3 by default, giving us 30 seconds for holding time. So normally, unless you go out and change these parameters, a node would declare a neighbor down after 30 seconds. The other interesting field over here is the circuit type, which will tell us whether this is a level 1, level 2, or level 1 and level 2, right? And then there's a source ID. The source ID here is the same as the system ID. We'll come and look at addressing, and probably that will be clearer. Then there's the holding time. We talked about that already, right? And then PDU length, which is the length of the whole packet data unit. And then look at circuit ID. Alright, so this is the other format for LAN, and I believe you guys can go and read about it somewhere. So let's save a little bit of time here. Some of the fields there are also the same that we have in the point-to-point in our packet. The only difference here is that we have a LAN ID at the bottom. Way at the bottom, there's a LAN ID over there. And all the fields are pretty much the same. Now, when we send hello packets on LAN, we want to target either level 1 peers or level 2 peers, right? So there are 2 addresses over there, all level 1 neighbors, or all level 1 ISPs, or all level 1 routers, and there's all level 2 ISPs, which also is the same as all level 2 routers, and the addresses are here, right? And so you just send this kind of broadcast or multicast to these addresses, and anybody listening on those at those addresses would be able to also respond, right? Basically, actually, nobody really waits for anybody. They just send, and there are some nuances that we'll talk about later on. Now, because of the way the hello format is and the TLVs that we use over there, we don't have 3-way adjacency formation by default in ISIs, even though it's implemented in Cisco and other implementations, and there is a draft in place today to support 3-way adjacency across different vendor platforms. But there is a TLV there we call IS neighbors, and this TLV allows you to keep track of the neighbors that you've seen or heard from. And so if I send hello and I receive hello from somebody, next time I send a hello, I put a neighbor's address in my hello, and so that neighbor knows that it's been seen by me, and that's how we do the 3-way handshake. On LAN interfaces, this is there, even from the spec 10589, because they have the IS neighbor TLV, and we'll look at TLVs, down the road also. Hierarchical routing, just like OSPF, hierarchical routing is supported here in ISIS, and we have 2 levels of hierarchy. So we've looked at areas before. This is pretty much the same slide here. We're showing 2 different areas here, 49002 and 49001. And the 2 of them have a backbone, meaning that an area where they will do level 1 routing. So between the 2 routers in the shaded area, they will form level 2 adjacencies, and then it would also form level 1 adjacencies with the routers in their area. And the routing that takes place in the clear circles will be level 1, right? And that's the hierarchical routing. Now the other thing that happens is that in ISIS, according to the original specification 10589 ISO, all areas must be stopped, right? So that means that no routes are leaked from the backbone into the area. So level 2 router hears an LSP from a neighbor, a level 1 neighbor. It takes those prefixes and puts it into the level 2 LSPs and shifts them across. On the other side, this guy gets the LSP and knows how to reach the other domain. But that backbone level 2 router over there doesn't send these prefixes into level 1 for the router on the farthest left to see where this route came from. What happens though is that any router that attaches to another area sets up a bit in the level 1 LSP that is called the attach bit. And level 1 routers look at the attach bit to figure out whether there's a level 2 router in the domain. And they point default to the nearest level 2 router. I know that was a little bit convoluted, but probably will be clear as we look at some of the configs. Okay, so here, hello, the packet types, right? So here we try to cover the packet types over here. There's not too many packet types, right, which makes ISS a little bit easy to troubleshoot from my personal perspective. We have just your hello packets to look for, and then your link state packets, right? And we talk about the hellos, LAN level 1, LAN level 2, and then point-to-point hellos. And then there's also your LSPs, obviously for level 1 routing and level 2 routing, different LSPs. So if you're part of a level 1 area, you do level 1 LSPs over there too, and then level 2 on the other side. And then there is there are this what we call sequence number packets, and there are two kinds of them, right? So the first one is the complete sequence number packets, which are just like your database description packets in the OSPF, and then there is partial sequence number packets, right? Basically, you don't really have to worry even about this other sequence number packets, the complete sequence number packets, and then the partial sequence number packets. All you really worry about when you're troubleshooting any problem is will be the link state packets and the hellos, right? And we'll look at that too. So it makes life a lot easier. The other interesting thing is that every node just sends one LSP, and it can fragment that LSP if there's too much information to send in there. So when you go out there to look at what the node should be telling you, you're looking at just one LSP most of the time. All right, this is probably the fun part of all of this. I'm just joking. CLNS addressing, right? So we know that anytime you configure ISIS for an IP network, you have to configure some other addressing scheme, and people kind of get concerned about that. Why do I have to worry about this addressing scheme? Well, the bottom line is that this is a borrowed protocol, and so that protocol requires you to have some other addressing. But the addressing is not that complicated, even though it looks like, and we'll go over some examples later on. I want to look at the concept of AFI values. AFI stands for Address and Format Identifier. We also want to look at requirements and caveats, some requirements and caveats that we need to follow to stay out of trouble. And then people have asked, so many times, how do I get globally unique, NSAPs? I mean, the question here is, do you really need them, for an ISP network? And we'll talk about this also. All right, so this is the format of CLNS address or CLNP address. Sometimes CLNS and CLNP are used interchangeably, but the protocol is CLNP, and the CLNS is the whole concept of ISO connectionless networking. All right, so there are three main areas in this address, all right? There's the area ID, system ID, and then the end selector, right? The area ID has another component in there called the AFI, and that really helps us figure out the format of the address. So there will be binary encoding and some other stuff that we need to kind of discern from the AFI, or who assigned the addressing, some domain-related information, right? But at the end of the day, for us configuring ISIs for an IP network, we don't really care about what the FIs are, right? We just go and get an address from somebody, or use the equivalent of private address in ISIS, and just bring them up. And we just have to delineate between the three three regions or three components, right? Your system ID is the 6 bytes that I told you about, the 6 bytes. Now, some people think it should be the Ethernet address, but on a router with multiple links, there may be so many Ethernet addresses. Which one do you use? There are ways that people use to define this system ID, and we'll go over one example. Then the other thing here is the N selector, right? And the N selector is equivalent in some sense, right, to a port TCP port number, right? And so in ISO addressing, you specify this N selector to indicate the network layer receiving entity, right? And in this case, if it is going to the routing layer, right, then you use zeros. Now, any address with zeros as N selector is called also a net, right? And so the AFIs, there's a lot more than what I'm showing here. I just selected this because this is what I've noticed most networks not to use, right? So there's an AFI of 37, 39, 47, and 49. We explained what they are at the bottom here. So there's X21 international plan for public data networks. This is what I kind of realized that most data networks really use, but there are other values out there. I've seen a lot of 47 and a lot of 39 and some 49s, and in some cases what people want to use private addressing. Now the 49 is local, right? So 49 means it's the same equivalent of private addressing, the 10 addresses that we know in IP. Right? So you can just take 49 and use, and nobody will bother you. Okay, so the caveats and requirements. We need at least one NSAP per node, right? So, I mean, that's pretty much obvious, right? So, and all routers in the same area must have a common area ID. So you can have a lot more addresses over there, a lot more NSAPs configured. You can have up to 3 by default, even though you can do a lot more. But you have to have a common area ID with another node for that node to declare you to be in the same area or accept you to be in the same area. Now, obviously, if you're in the same area, all nodes in the same area must have different system IDs, right? Now, in level 2, which is the backbone, all right, you also need the same concept over there, unique system IDs. Now, the simplest way to do this is to just give all your devices or nodes in the network different system IDs, right? But you can also play the game of having some nodes that are sitting right in the backbone using somebody else's system IDs in another area if that device doesn't belong there. And I know it gets complicated that way. But for simplicity, just make all your nodes have unique system IDs. Now, the very important thing is that in a given domain, all the system IDs must be the same length. So I can't talk to anybody else if that person has a different length of system IDs. And the reason why this happens is because when we start reading the system, the NSAP, we start from the rightmost, and we read the 1 byte N selector and then 6 byte system ID in our case. And so if it goes beyond that, then the whole concept gets kind of confused. So it has to be the same length for it to really work. So we'll talk about some of this, about multiple NSAPs being allowed over there. Now, if for any reason you wanted to do that, just make sure that the same system ID is repeated in the multiple NSAPs, right? And we can use this concept for merging two networks, splitting two different networks, and also renumbering, right? And I can give you an example, but we don't have too much time to do that. But supposing we have two networks, one of them was a different area ID, the other was a different area ID, then I can put two addresses on one node using the two areas, and the two of them would have been merged. The two areas would have been merged. Now, the maximum size of an NSAP is 20 bytes. It looks very long, 20 bytes, now compared to the 32 bytes of an IP address. And probably that's why it gets a little bit intimidating. But it doesn't take too much to figure out that if you just separate the N selector, which is 1 byte, another 6 bytes for the system ID, the rest becomes your area ID, and it's that simple. You don't even have to configure all the 20 bytes, right? Even though some people do because they have registered addresses, you don't have to configure all of that. On Cisco, for instance, you can do just 8 bytes. 1 byte to mean the N selector, another 6 bytes for your system ID, and then 1 byte will be your area, right? The recommendation is to probably not mix up your area with your AFI. I mean, we want to always have the AFI as a unique component in there, right? So if you decided to do, say, the local or private addressing with 49 as your prefix, just add one more byte so that you can have 2 bytes for your area prefix, just to make sure that people understand what you're doing. But all you need is just 8 bytes to configure an address on a Cisco router, for instance. So here are some examples here. Here we show 47.0001 and then 4 A's, 4 B's, and C's, and the zeros, right? And it's not that simple to figure out that. I take out the zeros for N selector, another 6 for my system ID, and the rest will be my area. I don't even have to count it unless there's confusion and I want to make sure that they match, right? And then this is another example here with a 39 prefix, and then that's another example, local ID, right? In this case, it doesn't have to be, your system ID doesn't have to be a MAC address. You can put anything there, right? Just make sure you know what you're doing. Now, how do people really define their system IDs, right? They don't have to go and get a MAC address from their router, right? The router may even not have Ethernet on it, right? And so how do you come up with one? What people do is normally you need a loopback address for your BGP or whatever you have, right? So they just take the loopback address. So in this case, we have 192.168.3.25. They take that loopback address, change it into something else, represent it like we would have on workstations, Windows NT or Windows 95, pad it with the zeros, all right? So here, 192.168.3.25 changes into 192.168.003.025, right? And with this, we already have the number of digits that we need to get a complete system ID. So this then becomes the NSAP at the bottom, 49.001 being the area prefix. The 192.168.003.025 becomes the system ID, and that's what most people do. And they can always follow this as an orderly way of doing things and then extract their addressing that way. Other people just pad the loopback address with zeros. But either way, it doesn't have to be a MAC address, and what you want is a consistent way of being able to figure out what your system IDs should be and what they are. All right. So the other interesting thing here is people want to know where to get addresses from. All right. Myself, I haven't owned a network before, so I don't know where to go get this from. But I just noticed that, or I did some little bit of research and found out that these are normally given out by international. For instance, there is the AFI 47, right, which is specified by one ISO document here, 6523. ICD stands for International Code Designator, right? And so there is an international registration authority which mandates authority to some sponsoring organization, and they go and allocate these addresses from what they are given by the RA, right? I believe the RA is sponsored by ITU. If anybody knows better, let me know. And so there is, for instance, the National Institute of Standards here, the United States National Institute of Standards, which has been allocated 2 IDI values, right? IDI stands for Initial Domain Identifier. So this organization has 2 IDIs, 005 and 006, and then that becomes part of the prefix of their address, and they can locate addresses from that space. And I'll show you an example. And then there's also AFI 39, which is administered by NC, right? Now the other group that I forgot to mention here is some subsidiary of the British Standards Institute, which deals with these IOTA addresses, I think they call them, identifiers for organizations. for telecommunications addressing, right? And they have an IDI of 0840. So on the next slide, we show you an example of this. For instance, these IOTA guys, right, belong to the International Registration Authority, right? They are affiliates over there, and they have 0124 to use, right? So they have a prefix of 47 to identify where they come from, all right? And so we have the 47, and then their IDI comes in there right after the 47. So the whole address is 20 bytes, and so you have the 47.00124 as a prefix. The next 3 bytes, is that right? 3 bytes, I think should be. The next 3 bytes should be 3 bytes. I think I missed one digit over there. Will be your organization ID. So if you go to them and then get an address, your ID will be 3 bytes over there. And then the rest will be assigned, 14 bytes will be assigned by the organization, as they want it to be. So if it is, for instance, the military, they may have so many different organizations, and they can use, or it could be the government, with various departments, Department of Justice, State Department. They can all have their own addresses within that, org assigned, space. And then comes your system ID, and then your end selector. Always, very consistent over there, 7 bytes, 7 trillion bytes. All right. So the other thing here is that does it really matter to have a unique address, right? And my personal answer is that if you run an ISP and you're using ISIS and you don't really have to share your ISIS information with any other ISPs, you don't really need that. You can use private addressing, right? The unique addresses make more sense for, say, telecommunications devices, that share information, say, between MCI and, AT&T or some local telecommunications company, telco. Then they would have to be unique devices, and when you do their signaling and all of that, that probably works very well for them. But you can simply use 49, and this ISIS is constrained within your network anyway, right? The only way you communicate with the outside world is by BGP. So you never really have to talk ISIS to anybody. Your 49, remains intact. Just choose an area prefix that can allow your network to grow very large, right? So I'm not sure the largest number of nodes we have in an ISP network, but I've heard, in the range of 500 and above, right? Anybody who runs an ISP here with more than 300 nodes, or nobody? Okay. All right, so the other thing we want to talk about here is the link state database. And the link state database is very, very critical. It's very important to understand how the link state database works for you to understand how ISIS works, right? I guess it's at the heart of the protocol. So here we'll look at what are link state packets, the data information units that are sent out with routing information between ISIS routers. And then we talked about sequence number packets before. We said there were 2 kinds. One of them is the CSNPs, complete sequence number packets, and then there's also the partial sequence number packet. And then we'll go on to talk about metrics, why we have metrics that we have on most networks today, and where we are going with new metrics. And we'll talk about flooding process. How do we really share this information? I mean, if I build an LSP that describes my local, my immediate environment, how do I share it, right? I do that by flooding. So we talk about flooding and how it works. And then look at some parameters, right, that go along with that. Every routing protocol has lots and lots of timers, and we'll look at some of those timers. And then we'll touch very briefly on the SPF algorithm. I wanted to do an elaborate kind of walk through how SPF works, but we don't have enough time for that. I believe that Radia Perlman is a good reference for understanding how this algorithm works. All right, so as a link state protocol, there is this notion that everybody captures their immediate environment and they share this all over, right? And so, for instance, router C in this picture here creates an LSP describing itself, its nodes, its connected nodes, and then links, right? And then sends this information in what we call the LSP. Everybody does that. And in an area, everybody must receive this information. We call it synchronization. Once you get this information, you have a complete view of the topology of the network, and then you can run SPF over your database and then come up with the optimal path to the various destinations in the area. Right. And so it looks like a jigsaw puzzle, right, where everybody brings a little piece, and then you have the complete picture, right? So the other thing here is that it's very important to understand what the route information packet looks like, and in particular the notion of type length values, right, TLVs. And so every packet, ISIS packet, has a fixed header, and then there are a bunch of TLVs, special information fields appended. And so this is what an ISIS packet will look like, and it's the same as other packets. The format is generic here. And so we have the intradomain routing protocol descriptor, which we said was going to be 0x83, and all the other fields being the same up to the maximum area. And then for each type of packet, whether it's a CSNP or PSNP or LSP or hello, you have specific header fields, right? And this is why knowing the length of the header gets important. And then you have appended TLVs, and there are so many TLVs out there. The IETF is working on proposing new TLVs to make the protocol work better. So we'll look at some of those, right? So in particular, the LSP format is shown here, and we show that up to maximum area addresses, right, is where the header information is common or generic. And then there's the PDU length, which comes in some other packets, in a different, probably byte location. And then there is, so the key thing here for an LSP will be the remaining lifetime, the LSP ID, sequence number, packet, and a checksum, right? The remaining lifetime tells us how long to hold an LSP in a database, right? And then there's the LSP ID. Obviously, every LSP must have an ID, and we're going to look at the format for the LSP ID. We want to be able to check against corrupted LSPs, right? We want to make sure that we don't really work with corrupted information, and so we have a checksum over there, right? And then there's this other field over there. There's a partition bit that is really not supported, but what it was designed to do was to allow you to fix a partition area by connecting through the backbone, right? And that is not supported, to the best of my knowledge, in any implementation, and certainly not in Cisco. And then there's a attach bit that we said that level 2 routers have to set, right, in their level 1 LSP, so that level 1 routers will know that they are connected to the level 2 backbone, right? And there's this other field of database, LSP database overload. If, for instance, a device gets overloaded for any reason, maybe lack of processor resources or memory resources, they can set this bit, meaning that people should not calculate routes through them, right? Because they wouldn't be able to forward packets. But packets, destined to them can be forwarded to them. And then the IS type, right? Whether it's a level 1, level 2, or level 1 and 2 together. And then the TLVs, right? So the LSP ID looks like this, right? There is a system ID, so each router generates one LSP that can be fragmented into multiple LSPs. And so the router puts in there the system ID, which is got to be unique, right? Remember we said the system ID has to be unique within the area, right? So within the area, that's for level 1 routing. And within the domain, that's for level 2, right? And so the system ID is here. There's another field over there called a pseudonode number, right? If it is non-zero, it means this is an LSP generated by the pseudonode or the disk for some emulated LAN, right? Some virtual LAN over there. Not VLAN, but some LAN, emulated as a node, pseudonode. And then the last byte over there is the LSP number. If it is non-zero, then obviously this is a fragment of the LSP. So this implies fragment. This is the fragment number, right, or fragmentation number, I should say. Right. So if it is not, so here what we are showing here is an LSP generated by the pseudonode, right, for some link LAN number 2, right, and then this is the second fragment, right. So the original LSP itself, the first fragment would be 0, 0, and this is 0, 1, right. Okay, so the other packets that play in the database are the CSMPs, and here we have the same format here, a fixed header and TLVs, right? And we show that there is the information that we put into CSMP is summary information, right? Because what the CSMP is doing is providing us summaries, right, of all the LSPs that we know about. And so we have 4 important pieces of information in there: the LSP ID, remaining lifetime, sequence number, and a checksum. This information is enough to describe an LSP completely. So what we're going to do is that anytime we send out a CSMP, we'll put in this summary of all the LSPs we have in our database, right? And then there are also PSMPs, which are the same. They look and feel the same as the CSMPs, except that these don't have complete information of everything that we know about. It's just some specific information. It has information about specific LSPs. And we use it in 2 ways. One for acknowledgement. So what we do is on point-to-point links, the LSP exchange is by a very reliable mechanism. We say flooding is reliable on point-to-point links. So if I send an LSP, I need an acknowledgement that it's been received. On LAN, on the other hand, we don't do that, and we'll look at flooding later on. So this is a list of TLVs over here, and this is for level 1. So if anytime I generate a level 1 LSP, these are, as a matter of fact, these are just all the LSPs that would be available for level 1 packets, right? So hellos could use some of these LSPs as well, right? And some of this information are also in level 2 LSPs. And so what I've done is highlighted the information TLVs that are specific to level 2, and then information that are specific to level 1. And then there are new TLVs here which are supposed to make our lives easier. A lot of it, for extensions, ISIS extensions for traffic engineering, MPLS traffic engineering. So there's TLV 20 type 22, router ID TLV 134, 135 is a very big one, and then there's 137, and then 240 for point-to-point reliable distance information. Now metrics. ISIS has, so the original spec, right, specifies 4 types of metrics. So there is the default that everybody must support. There is also a delay metric and expense as well as error, right? And we explain all of them here. In reality, nobody implements anything. I don't know whether anybody is trying to do anything else, but Cisco doesn't implement anything else apart from the default. And the default is what everybody must support, right? So the other metrics are optional, and they are intended for class of service routing, which is taking a different, kind of, trend with IP. So nobody really does these other metrics. Here we show the TLVs that have metric information. So your IS neighbors TLV, your ES neighbors, your previous neighbors. For us, routing ISIS for IP, we would care more about the IP internal reachability information, and then the IP external reachability information, and the extended versions for traffic engineering. And so this is what a TLV would normally look like, right? So this is the I believe this is the IP reachability TLV. This IP internal reachability information. I believe external reachability has the same format also. But the key thing we wanted to point out here is that we have the default metric, right? So we have 4 bytes, to represent metric information. 1 byte for the default, and then there is 6 bits reserved for the value, right? The IEB stands for whether this is an internal or external route, and then there's 0 for the default metric, meaning that it must be present, right? Now for the other guys, if you set the metric, if you have the delay metric in an LSP or in a TLV, then you 0 the S bit, right? So with this format, right, we're looking at just the default metric, right, in the old metrics. With this format, we end up having a total of 63 possible maximum per interface on a router, right? We have 6 bits to play with, given a 63. Then there is a protocol constant that says that your maximum length of a path has to be 1023. Right, so you can't go beyond 1023. So you can assign multiples of 63, and just like OSPF, we calculate our routing information by the total the total of the metrics on all outgoing interfaces between the source and destination, right? And so 1023 is the maximum we can have, right? Which is probably a limitation, right, for some people. People want the convenience of assigning any metrics they want. And there is no automatic assignment of metric, based on bandwidth. So we can't go and read the bandwidth and say, okay, because of this bandwidth, this is going to be a metric. So it has to be manually done, which gets to be a pain for some people. Cisco's use 10 on all interfaces. Okay. All right, good. All right, good. All right, so we're taking a break. So it looks like we okay, good. All right, so here we wanted to talk very quickly about the flooding process, and since we're only a little bit out of time, we'll be a little bit quick here. But I wanted to mention that on point-to-point links, the flooding process is reliable. You send me an LSP, I need it acknowledged. On broadcast links, on the other hand, it's not really reliable, but there are other ways to do it so that we can achieve some level of reliability. And the way we do it is to do periodic flooding, right? And periodic flooding doesn't mean that we are sending the LSPs all over again. What we do is we send the CSMPs. The disks on the LAN or the broadcast network will send CSMPs periodically. And then there are 2 flags that really help this flooding and synchronization process. One of them is the send routing message flag, and the other is the send sequence number flag. So anytime you send, so if I receive an LSP from one link, I set the send routing message flag on all the other links that I need to flag out of. And then if it's a point-to-point link, I set a send sequence number flag for acknowledgement. And we'll look at examples here. Here is a case where we have router A, B, and C. So we receive an LSP router RTA.00.00 from router A, right? So router B sends an acknowledgement back with a PSNP, right? On the other side, though, router B has to forward this because it's a flooding mechanism, and everybody in the area has to see the LSP. Router B has to flag it out of interface 3 to router C. So router C gets the same LSP, nothing is changed on it, the same LSP, and then sends an ACK back, to router B. Right, so that's how you achieve reliability in flooding over point-to-point links. In this other example, the slide looks a little bit crowded, but what I wanted to show there is that we have RTX, who sends an LSP, RTX.00.00 to router A, right? Now router A is connected to a LAN, and it happens to be the disk over there. So normally router A will still have to flood it out, regardless of whether it's a disk or not. But the first thing router A is going to do is to send an ACK back to router X, right? So it sends an ACK back, says, okay, I've received the LSP. And then A turns around and then flaps this out to the LAN, right? Just by being a router, not because it's a disk, right? So it flaps this out to the LAN. And for some reason, there was some hiccup over there. That LSP didn't make it, right? And so router B and C didn't receive it. So router B and C still don't know about RTX, right? And so because router A happens to be the disk on the LAN, it's going to have to synchronize databases in the area by sending periodic summary, right, which is we call a CSMP. So the next time the timer kind of kicks up, it sends a summary, a CSMP, and it says, I know about router A, B, and C, and D, and it sends summaries over the LAN, right? And it's doing this on just the LAN. Then router B and C come up, and say, hey, it looks like the information that you're sending us has one guy over there that we never really saw, right? And this guy is router X. So I don't have router X over here, but it should be router X, right? Instead of D, we should have RTX, right? So these guys come back and say they send PSNPs back requesting router X's information. And router A then goes back to send the LSP to them. So this is something that happens on the LAN, right? And this is just because router A happened to be the disk, and it happened to be sending the periodic, flagging, right? So it's not like you're sending the whole set of LSPs. You're sending just a summary of them. And so this is how synchronization is done on the LAN, and it's done periodically, and it doesn't really take that much, right? So a couple of timers here. We have the max age, which is 1200 seconds. We have the LSP refresh timer. Max age is the longest time an LSP can live. If I generate an LSP, I set max age on it, right, for 1200 seconds, and then flat it out. And the timer just keeps going, right? When the timer gets to 0 and there's no newer LSP, I wait some other interval, they call it 0 age lifetime, and then throw it out, right? But there's also this concept of refresh, just like other protocols try to do. So 15 minutes into that time, every router generates their LSPs again. So after shipping my LSP out, it would have aged in 20 minutes. 15 minutes, I try to refresh the whole network with my LSP, right? And this is all kind of done with timers and jittered in a way that there will be no immediate rush of everybody trying to update everybody, right? And then there's also this LSP transmission interval, meaning that the maximum time interval between two consecutive LSPs has to be 33 milliseconds, right? And then there is a retransmit. So if I send an LSP on a point-to-point link and I don't get an acknowledgement back, I retransmit it back on the LAN, and I keep doing that until I get an ACK back. And so this is done every 5 seconds, and that can be changed with the command on the right-hand side as well. But all of these timers kind of go along, which will affect the convergence, how quickly we converge, right? Some of them are constraints, some of them are time constants, protocol constants that we have to adhere to. Most implementations have made this kind of configurable in some way. But for the most part, when you turn up your routing, it's mainly the default, right? All right, so the other thing we wanted to talk about very quickly here is having gotten the whole database that full of LSPs in the network, right? We will periodically go and run the Dijkstra algorithm over it. The Dijkstra algorithm is also the shortest path algorithm, shortest path first. And it's the same algorithm used by OSPF, right? And so we build a link state database, and we run Dijkstra over it to determine our best path, right? Then here we are saying that we run separate SPF processes for level 1 and level 2 because there are two different databases. The information in level 1 may not be the same in level 2. So different processes are run, right? So generally we run SPF no more frequent than every 5 seconds. So if there is any change, so suppose an SPF was run and then there is a change and somebody sent a new LSP, I can't really go back and run SPF. I have to wait for 5 seconds before I can run it, right? This timer can be changed. There are commands within Cisco IOS to change it into different value. And we know that SPF will run when topology changes, but you have to wait for this timer, right? Whatever the default is. And then for leaf elements like IP prefixes, so the other thing to have in mind here is that when we run ISIS, our topology is determined by the nodes, right, the routers, right? Of course, we know about the routers via links, but we are mainly kind of hinged on the nodes, right? And so for IP prefixes on a link, which is a leaf link, it becomes what we call we call it leaf links, right? And they don't really impact. I shouldn't say they don't impact, but when we lose the leaf link, right, we run what we call the partial route calculation. And this also happens in other protocols like OSPF. Also, you run PRC. Probably the difference between OSPF and ISIs is the fact that OSPF, is built on IP links, right? So it's watching subnet, right? And any change in subnet, in an area may probably create a little bit of a change. In ISIS, when there's a change, that link drop should cause a topology change for us to really worry about it, right? So, for instance, in OSPF, we have inter-area route, so if a node in an area sees a change, right, of an inter-area route, it runs something similar to PRC. If an external route changes, we do the same thing, right? It just happens that the way ISIS works based on nodes, right? PRC is much more pervasive, and it saves a little bit on processor time and other things. It's not any significant advantage about OSPF. Just a point to just make, you guys aware. So the PRC evaluates only the routers have changed, and they are really quick and less CPU intensive compared to a full-blown SPF. Right. So a couple of points about things that would affect the rate at which how much demand your SPF will be on the system or in the network, ultimately affecting convergence, right? But we also know that there's a couple of timers involved. Some of them default timers, some of them protocol constants, and this go a long way, to really affect how things work and how we get our convergence. The number of nodes is critical. The number of links involved, right? How many of these are going to be leaves, right? Number of IP prefixes, for that matter, right? Because it could have multiple IP subnets, secondary addresses that we need to track. And then the degree of mesh for non-broadcast multi-access networks, degree of mesh becomes very important also. And then your route processor also gets to play here, because if you have a slow route processor, that would go to affect, how quickly SPF, would complete every round, right? All right, so that's about SPF, and I wish I had time to show how it works, but probably let's visit Radio Perma and see how it works over there. The other thing we wanted to talk about was extensions for MPLS traffic engineering. First, most critical one was wide metrics. Because of the way the protocol was designed with 4 metric fields, 4 bytes metric field, 1 byte, had to be used, for default, and the other was the class of service or quality of service, metrics. There was always this waste of space that nobody really implemented, right? So what some folks in IETF did was to change the rules a little bit and go and access these fields and then use them as metric fields, right? And so the default gets extended, larger. And then there's also sub-TLVs that were introduced basically to carry MPLS resource information. And so here we see 2 significant introductions into ISIS. One is TLV22 and the other is TLV135. Right? And so in TLV22, the metric field has been increased to 3 bytes, and in TLV135, which is the IP reachability TLV, the metric field has been increased to 4 bytes. Right? And we'll look at the format here. So for the extended IS reachability over here, this is the breakdown. You can look at them for yourself. This is more interesting for us here. If we don't care about MPLS and we still want to use ISIS for routing, then this TLV is more important for us. So we can configure the physical routers or whatever you have to use wide metrics, meaning that this is going to be how you will be building your LSPs, right? And so the length is still a 1 byte field, and that gives up to 255 bytes for the total TLV. And then there's 4 bytes of metric information, right? And then some control information and stuff like that. But bottom line of all of this is that you get a lot more space, right? A lot more bits to use for your metric. Right. Sub-TLVs, basically to help the MPLS use of ISIS for traffic engineering. Network design considerations, right? So the first one to talk about is suboptimal level 1 routing, right? And the second thing will be layer 2 domain-wide prefix distribution, which allows us to fix the first problem right? Suboptimal level 1 routing. And then we'll talk about NBMA networks, or fully meshed networks with a very high degree of meshes, how to get around, that, especially ATN multi-point networks, not multi-point, but ATN mesh networks. And then we'll talk a little bit about routing convergence also. So here, we learned from what we've studied so far, or discussed so far, we know that ISIS are specified, by ISO 10589 and RFC 1195, makes all areas are stops. And so if you're a router which is doing just level 1 routing, you're sitting within an area, you can't really have accurate information about how to really exit from your area. And we'll look at slides that explains that. And this is because no level 2 router leaks inter-area routes into level 1, right? And so in this picture here, we show area 49.001 with 2 routers over the router C and router D, right? And these routers are both level 1, level 2, connecting that area to the through the backbone to the other area, right? And we understood that RTC, RTD, and RTE happen to be level 2 routers because they are connecting to some other router or other routers in another area, right? Now these other routers, router A and B, could be really small, 2500 routers or some other vendor router, and so we wouldn't really want to tax them too much and let them run 2 levels, right? So we make them level 1 only. But if you did this in the based on the old way of doing things in ISIS, this will make RTA and RTB stub routers, and they can only point a default out to one of these routers, whether RTC or RTD, to get out to the other domain, right? They don't know about the prefixes behind RTA, for instance, right? They have to go to the nearest router to go, level 2 router to go out. And so they make a determination over here which of these 2 routers, C and B, is nearest, right? So they look at the metrics. One has 10 going out to router C, right? So for instance, router A says, I have 10 going to router C to get out of the domain, or not the domain, the area, right? And it says, okay, I have 20 to get to router D. Both these routers are advertising themselves as level 2 routers because they said the attached bit in the LSC that they sent me. And so they are level 2 routers. And so if I need to get to an address which is not in this area, I have to go to one of them. But then we also know that there's a better link, OC48 link, between router D and router E, right? Which is far, a bigger pipe than from router C to router E. So by pointing a default to the nearest level 2 router, RTA may not be choosing the optimal path to get out of the domain. And this is just an example, and so there may be some, it's just to illustrate, the point. So don't read too much into it, right? And so how do we really fix this, right? So you have to go in there and then change the metrics and make sure that RTA prefers going by router B, right? And this could be so many. There could be so many of such situations in your network that you get tired of it, right? And the simplest way to fix this was to put all your routers in one area, right? And the challenge is that will they hold, all working in one area, right? And so, fortunately for ISIS, that seems to work quite a bit. I'm not sure that because of the pervasive partial route calculation, right? But people wanted to use ISIS, for historical reasons or whatever reasons, they decided to use ISIS. And they found themselves stuck in this situation, and they had to lump everything into one area. And for some reason, it worked, right? OSPF, on the other hand, will require you to build hierarchically and nicely in a kind of network, design network, and that would scale and probably last you a long while. And so this is a problem within ISIS, as it is until recently, right? And so you put everybody in one area, everybody sees everything. So an LSP from router F comes all the way through, right? And so you have 2 choices here. Are you going to let all of them run as level 1 and 2 together and then keep 2 separate processes for the same information? So what people do, again, is they go around and turn off either level 1 or 2, right? And so some networks have turned off level 1, some other people have turned off level 2. And the question here is, I mean, why would you turn off one or the other? I mean, anybody can answer why you should do level 2 only if you have to use this solution as a workaround, the stop area problem. All right, so people use level 1, right? And because they were thinking about the fact that if you are all in the same area, then you got to be doing level 1. But in reality, you can also do level 2 and all be in the same area. And that was a smarter way to go doing level 2, because you can then go turn around and append other stop areas to that level 2. So most networks, I don't want to mention names, but most networks did level 1 when they implemented this way back. And more recent networks, that decided to use ISIs, went level 2. For instance, the customer we just converted, to ISIs, did level 2, right? They also did wide metrics, which is also a good thing. All right. Any questions so far? I haven't stopped to ask if you had any questions. All right. So the other way to fix this is to use this spec that this IETF draft recommends being able to link inter-area routes into areas, right? Just like OSPF does it, right? And so it's also known as route linking in Cisco parlance. It's known as route linking, and this allows level 2 routers to just take the inter-area prefix that they learn from their level 2 peers, right, and then send them into the area. That way, from this picture, the RTA, RTB would have good information and then make a judgment based on the metrics about the best way to go out to get to a prefix. Right, so in the future, people can now start building hierarchies into their network, right? The other thing I wanted to talk about was problem with flooding, right? Flooding becomes a pain if there's a little bit of churn in your network, flooding takes bandwidth, right? And so people want to be careful about how they flood. And so in this scenario where you have a non-broadcast multi-access connection, for instance, like ATM or frame relay connection, the recommendation is to go ahead and do point-to-point links between the routers. And when you go ahead and do these point-to-point links, what's going to happen is that you have RTA and RTB, RTC, and D all meshed, all right? For some reason, you couldn't mesh RTE, so they stay on the side, all right? Now, if we look at the fully meshed RTA, B, and B, C, and D, anytime an LSP is advertised by A to anybody, any of these B, C, and D over there, those other routers will turn around and advertise them back out to the other peers, right? And that could be an order of like N-1 unnecessary flooding, or N-2, I think, based on the number of nodes which are appearing over there. And so there's always going to be redundant flooding, right? I mean, if we are fully meshed, and I'm router A, and I sent router B an LSP, I sent an LSP to every one of my peers, they should have received copies, and they shouldn't care about receiving from anybody else again. So the whole idea here is that, can we really eliminate this redundant flooding by putting router A, B, and C, and D into a mesh group, right? And the way mesh group works is that when you receive an LSP from a member of a mesh group, you don't send it to the other members. And it's just a simple configuration that you put on, you define a mesh group number and then put that configuration on all the routers, and then they become members of that. That works very well, and it has saved quite a lot of networks, especially with ATM in the core from melting down, right? And this, so that has been around for quite a bit, at least within Cisco, but this is a recent draft to make it much more, as a standard for people to implement. The other thing we wanted to talk about very quickly here is that today most people configure their networks, and what they're looking for is stability, right? They know that they want convergence, but stability is probably more important than anything else, right? So they want to do faster convergence, but you have to be careful. And what we are saying is that was times of the past. Today we have optical links, very clean, circuits. When they work really great. And so there's no point to be really worried about all these timers which are supposed to keep stability. When we looked at SPF, we saw all those timers over there with a go to the SPF timers, database timers are all oriented towards stability, so that when there's a churn, there's not too many processes running, which would eventually cause a meltdown. Because when your routers run SPS too frequently, too much processor requirements, and you have a network meltdown. So we believe that today, with the better quality of circuits out there, we don't have the X25 analog circuits any longer. We can do probably, we can be a little bit more bold and be more aggressive with our timers so that we can converge a little bit faster. Now there are risks involved, right? So we know that our circuits will stay up, but what about if they don't? Just in case, that one day things go really bad and they didn't stay up, right? So you're going to have constant generation of RSPs, right, costing you lots of bandwidth, right? There's going to be too much flooding going on, and there'll be SPF running, right? If you're not lucky to have some of these being leaf, entities like say IP, edge links. You end up running full SPF. That would cost you quite a bit, right? So what we know today is that with the implementation of partial route calculation, we've really pretty much reduced the challenges that come with SPF runs when there's a churn. We also know that with the case of say fully meshed networks like us in the NBMA, non-broadcast multi-access switches, we can reduce the level of flooding, right? And that would probably also help. Now today, most high-speed routers have implemented what we call distributed forwarding, or they have separate forwarding. I mean, they have forwarding separated from the routing engine, right? So you have a routing engine or a route processor, which does all its system monitoring and route calculation, and doesn't really care about who is doing forwarding right there, right? That is done by either multiple distributed, kind of forwarding, or some very high speed, ASIC doing central forwarding, right? The two processes are all separated at this point in high speed routers. So we can also go back and leverage these gains, right, to be more aggressive, right? And so how do you do that, right? The way to do that would be to reduce your timers, because we are held back by the timers a lot. The timers want stability, but they hold us back. So we can reduce the timers quite a bit, right? For instance, we can run SPS no frequent than 5 seconds. Can we be more aggressive and run it, probably every second there's a change, right? But then you can't continue that way too, because if there's a change and you run SPS, and that continues, right, you may really run into a meltdown. So there's got to be some intelligence built into this to allow the process the situation to stabilize when the churn is persistent, right? So I can be aggressive, and then all of a sudden I realize that the situation is that bad, and I can back off, right? And so there's a lot of work going on within Cisco to address these opportunities, to have faster convergence, realizing the fact that there is better quality links out there. And so 12.1 code, Cisco code, for those of you who have Cisco's, would have these features. And these give up to probably around 8 times faster convergence than your normal SPF stuff that you will see in 12.0 code. But obviously this will be meshed in there as we move on. And so you can get other, probably, I don't want to give any figures, but you can get pretty much low figures, for very high number of nodes in your network. And the interesting point is, what is the largest size of networks that you guys will have noticed out there? Who has a network which is more than 500 nodes? Or 200? 200 you do? 500? Would you mind to give the name of the network? Oh, in media. Oh, cool. Anybody else with more than 500? Right. So, even though these capabilities, the code is there, it's not in 12.0s. Most ISPs have configured for reliability, and I'll show you sample ISP configuration as we look at the configuration, sample configurations. Okay, so we're ready for basic configuration, all right? And I said also a disclaimer to these configurations. They do work, but if you try to configure them, make sure you go to the Cisco reference manual to make sure that they are the right commands. We also have on the web configuration, the interpretation of these configurations from other vendors, and I believe we have from Redback, configurations from Redback, and also from Riverside over there on the NANOG page. So if you would, if you have any of these routers, please feel free to look at them and compare them. Most of them are very similar to a large extent in terms of the CLI. So, but take a look at them if you have any of these routers, other routers. All right, basic configuration of ISIs. It's as simple as, as you see here, two routers, GSR2, GSR4. There's also GSR1 in the background. But we're looking at just GSR2 and GSR4 talking to each other. What do you need to do to enable ISIs on there? There's nothing much to do. First of all, you have to figure out your NSAP, which we said was very easy, 49.something, and then you have an NSAP, for yourself. The NSAP doesn't have to be any complicated MAC system ID. You don't need any complicated system ID over there. You can have, for instance, in the case of GSR2, we're using 0000.0000.0002, right? It's as simple as that. And then we need the trailing zeros over there for the end selector, right? And so here, what do we show? We show GSR2 in one area. If you take away the 7 trailing bytes, right, the rest becomes your area. So our area ID here is 49.001. On the other hand, if you go to GSR4, GSR4 has another area. It's in another area, and the area ID there is 49.0002, right? Now and so this is the most painful part, probably, right? But if you have a loopback address and you do the conversion, which I didn't do here, and you do the conversion and then determine what your NSAP is going to be, the rest is just a matter of just going to the interfaces and applying, IP router ISIS for your process over there. So first of all, we configured the router process. I should call it router process or routing process, I should say. And we gave it a tag, right? The tag is SJ, standing for San Jose, where I live. But it could be anything, right? You can have, if you have intermediate, for instance, you can use INT or INM or whatever you choose to use, all right? But it's just a tag, right? It has local significance. And then you configure your net. You've already enabled the process, right? And then you can then go on to and apply this process to the interfaces. So unlike the other routing protocols which require you to have a network statement which covers the interfaces on which you want to route, here you just go and apply the process to the interfaces, all right? So it's a lot simpler, right? I don't have to figure out, my network and then reverse the mask and all of that to make sure that all my interfaces are covered. And so you go to the interface, for instance, on loopback 0, you do IP router ISIS SJ, and you're done. So how do you really see if this is working, right? Shows LNS neighbors, right? Gives you your neighbor status. And so we said that this is configuring ISIS. We want to configure it for IP, right? But we also run into this CLNS because of the underlying construct of the protocol, right? And so GSR, we see two neighbors over there on router 2, GSR2. We see GSR1 and GSR4. We see the interfaces they connect to. There's also the SNMPA, which is a subnetwork point of attachment. We said it was a data link interface. We see a MAC address over there for GSR1, which connects to a MAC to an Ethernet, and then HDLC there. There's no number over there. These are tracked with internal interface descriptor blocks within system. And then we see a state, which should be up, right? And the whole time tells you how long before you declare the neighbor gone, right? So, for instance, in the case of GSR4, I'm waiting for their hello in 25 seconds, and this is timer which is like decreasing, right? So when it gets to 0, if they haven't sent me another hello, I just throw them away. And then there is the type of connectivity, right? So it's either level 1 and level 2, right? So you can do, normally when you go and turn up a Cisco router, it comes up as both level 1 and level 2. And the reason why that is very critical is because if you're not very careful, you could end up in a situation where your level 2 backbone is not really contiguous as it should be. And so you come up as level 1 and 2, and you can go back in there and then take one of them off if you want, right? But when we connected to to GSR4 over there, we came up as level 2 because GSR4 happened to be in another area, and the only way we could negotiate with them was on the level 2 basis, right? But on the Ethernet here from this picture, we were all in the same area, and so we negotiated both level 1 and level 2 then. Maybe if GSR1 is overloaded or it's probably, I don't know, I couldn't say it was a smaller router than the other router. If for any reason, I mean, you don't want GSR1 to be level 2, you can go and turn it off from the CLI. You can do a detail, all right, which gives you more details about the adjacency here. Another very important command that will really help you understand what's going on is to do the show CLNS interface command. When you do that, just like your show IP interface, it gives you some decent output like that. And if you go all the way down to the middle somewhere there, I don't have the laser thing, to show that. But if you go all the way to the middle somewhere, you see the circuit type, right? Is level 1 and 2 for the ports. The type is 1 and 2. That means we are capable of doing 1 and 2, right? But if you go further down, you see an active neighbor, right, who is level 2. So it says that number of active level 1 adjacencies on the ports is 0. The number of active level 2 adjacencies is 1, right? Because we just connected to GSR4 from there. And it gives you the hello when you're expecting another hello from the time we did this capture. Question? So the ESIS, we talked about that. That's the end system to intermediate system communication, right? And that normally is supposed to happen between routers and end systems, or routers and hosts. But when we come up, all right, we also exchange this between the routers. So a router will send an ISH to all hosts and also to all routers, right? And we actually need to hear the ISH in order for us to start sending hello. And that's why I said that they are tied. They're not really related, but they are tied into each other somehow. But you don't have to worry about that because once you enable ISIS, Cisco, in the Cisco's, that's enabled by default. I don't know how the other vendors do that. So the other interesting thing here is circuit ID, right? This is more interesting for the LAN interfaces. Okay, this is the interface for the show CLNS interface for Ethernet 0. You can also do show CLNS protocol, which is just like doing show IP protocol. Now, the interesting thing here is that we are talking about the CLNP protocol, right? The equivalent of IP, right? And we keep on doing show CLNS. But this is much more historical than anything else. Right, so this is what you see for the protocol. Nothing interesting here. The protocol comes up with a distance of 110, and so you know that Cisco distinguishes between routing protocols using administrative distance, right? And we come up with 110 over there. But for IP, our distance actually will be 115, right? As against OSPF, which is 110. So what else can we can do show ISIS topology. And the interesting thing is you can enable, when you enable ISIS, right, and CLNS routing comes up, if you don't need CLNS at all, you can go and turn it off also, right, and it will still work, meaning that you're just shooting for IP, right, and everything would work. Okay, what else is interesting here? Nothing much. Okay, so the other thing is that how do you really look at what's going on, right, and that means going to the database and looking at stuff in the database. I find it very, very easy and very convenient troubleshooting ISIS because when you go into the database, say for instance in one area, all the routers are there with one LSP, right? Unless there's so much information that they fragmented into multiple LSPs. But just by doing a show ISIS database on one router's LSP, you see every information that they have to put in there, right? Unlike the other case of, say for instance, OSPF where you have router links LSA and network links and a bunch of LSA, right? This is just one LSP that captures the whole environment for you, and it makes life a lot easy when you're troubleshooting. It's not a major plus, no problem. So right here in this LSP, we have the area address information. All right, so first of all, at the top of this information, we have what would have been the summary of this LSP, right? Stuff that we borrowed from the LSP header. And we are showing the LSP ID. We are showing also the sequence number, and we are showing the LSP checksum, right? And then the LSP hold time. The hold time we said was the maximum time that LSP would live in a database, right? And when it gets to 20 minutes and we haven't had any refresh, we wait another period, a little bit, 0 each time, and then we throw it out. Then here in this level 2 LSP, we see the attached bit set, right? As a matter of fact, this is a level 1 LSP. This is a level 1 LSP issued by the level 2 router, GSR2, right? And it says that I'm attached to somebody in another area, which is the GSR4, right? And this is how level 1 routers would be able to figure out how to come to this router to go out. And so this is another LSP here. Same output, similar output. There might be some minor difference over there. Oh, this is the same LSP. So this level 2 router, GSR2, is a level 1-2 router. And so it has two LSPs, one for level 1 and another for level 2. Right? And we are looking at both LSPs. This is a serial node LSP because it's connected to a LAN. There's somebody who's going to be the serial node, and that happens with GSR1. So we can look into that serial node LSP and see what's in there. Normally, it lists the routers that are on that LAN. Then you can go back and do your regular show IP route stuff, right? We have a couple of configurations here for ATM multi-point. Interesting thing there is that you just have to do the map list, right? You do the map list, and then you turn around and apply the map group, right, to the interface. And in your map list, you have to have two statements over there, one for IP and the other for CLNS. Similar configuration. I mean, these are outputs for this scenario here, ATM, the show CLNS neighbors, and then show CLNS interface. And then we have ATM point-to-point. This is the recommended thing to do. But by doing point-to-point, your mesh is going to be to a very high degree. Then we are saying go ahead and use mesh groups, right, so that you can limit your flooding. You can control redundant flooding. Here also is the CLNS neighbors when you do point-to-point. This is an example for frame relay. Same, for multi-point, you have to have a frame relay map for IP and a frame relay map for CLNS. This is the, so here we have the interesting one here, the configuration that you see in a typical ISC router. I don't remember where I got this from, but obviously this doesn't really show the customer information here, right? And so here, what we see is that most people do, so the default hello interval is 10 seconds. Every 10 seconds you send out hello, and this is also jittered, all right, in a way that you don't really send to, it doesn't get synchronized, all right. But people change that to 12 seconds instead. And it looks like it's getting time to the end of this session, and I'm sorry we had so much information there I couldn't talk about. So I'll use.
I really just thought we have a breakdown here, and people want to support.
Okay. All right. So I'm sorry, guys. Thanks for coming, and I hope you enjoyed the presentation.